Welcome to The Explainer. Today, we're going to dive into the epic story of a star, from its very first flicker in a cosmic nursery all the way to its dramatic universe-shaping finale. So, let's get right to it. This one question, it's the key to absolutely everything. A star's entire fate, how it lives, how it dies, is all decided by one single thing, its mass. And the rule is actually pretty simple. The more massive the star, the shorter its life. That, right there, is the central law of stellar evolution.
So, where does a star's story even begin? Well, it all starts inside these huge, dark, and actually pretty cold clouds of gas and dust, just drifting out there between the stars. These are the stellar nurseries.
And the scale here is it's staggering. I mean, we're talking about these things called giant molecular clouds. They're these enormous reservoirs of hydrogen and helium, so immense that they've got enough raw material to create not just one star, but whole clusters of thousands, or get this, even millions of them. So how does this all kick off? Well, it usually starts with some kind of trigger. Maybe a nearby supernova explosion sends out a shockwave that smashes into the cloud, breaking it into these dense fragments. Then, gravity takes over, pulling these clumps tighter and tighter. As they collapse, they heat up and start to glow. Now they're what we call protostars. The final step is ignition. When that core gets incredibly hot, we're talking 10 million degrees Kelvin, nuclear fusion finally kicks in.
And boom, just like that, with the very first fusion of hydrogen atoms into helium, a new star is officially born. It stops shrinking, it finds its balance, and it enters the longest, most stable phase of its entire life.
Okay, so this phase it just entered? We call that the main sequence. You can kind of think of it as the long, stable adulthood of a star. This is where it's going to spend the vast majority of its existence, just steadily burning through its fuel.
And get this is a pretty wild fact. About 90% of all the stars you can see in the night sky, including our own sun, are currently in this main sequence phase. It is, by far, the most common stage in a star's life.
So how in the world do they stay so stable for so long? Well, it all comes down to this perfect balancing act called hydrostatic equilibrium. Seriously, picture a constant cosmic tug of war. You've got gravity, which is relentlessly trying to crush the star inward. But at the same time, the immense energy from nuclear fusion in the core is pushing outward. As long as those two forces are perfectly matched, the star is stable. Okay, so we've got all these stars chilling in their long, stable adulthood. But, they're not all the same, right? So how do astronomers make sense of it all? Well, they use this brilliant tool, almost like a celestial census, to classify stars and figure out exactly where they are in their life cycle. It's called the Hertzsprung-Russell diagram, or, the HR diagram for short. And this single chart was an absolute game changer, because for the first time, it organized the chaos of the cosmos and let us see a star's entire life story in a single glance. So what is it? It's basically a graph that plots a star's true brightness, its luminosity, against its surface temperature. The brightest stars are way up at the top, the dimmest are at the bottom. And here's the part that's a little counterintuitive. The hottest, bluest stars, they're on the left, while the coolest, reddest stars are over on the right. And here's the magic. When you actually plot the stars on this thing, they don't just scatter randomly. No way. They fall into these really clear regions. That long diagonal band running through the middle, that's the main sequence. Up in the top right, you've got the cool but super bright giants and supergiants. And then down in the bottom left are the hot but really dim white dwarfs. And you know how astronomers remember the order of that temperature axis? There's this classic mnemonic device for the spectral types, which are lettered O, B, A, F, G, K, M. O, be a fine girl or guy, kiss me, helps you remember them from hottest, the O-type stars, to coolest, the M-type stars. Our sun, by the way, is a G-type star, kind of right in the middle. But of course, that stable main sequence phase, it can't last forever. Once a star burns through all the hydrogen fuel in its core, its time is up. And what happens next is this dramatic fork in the road. And it all comes back to that one single thing we started with, mass. Think of it this way. Low-mass stars, they're like those super fuel-efficient economy cars. They just sip their hydrogen fuel slowly, and they can live for billions and billions of years. High-mass stars, on the other hand, are the gas guzzlers. They burn through their fuel at an absolutely incredible rate, shining super bright, but living for only a few million years. It's the classic live fast, die young story. So for a low-mass star, like our Sun, its final act begins when it swells up into a red giant. Its core shrinks and gets hot enough to ignite helium into carbon in this sudden, violent event we call a helium flash. After a while, its outer layers just kind of drift away into space, creating this beautiful, glowing cloud called a planetary nebula. Kind of a misleading name. Early astronomers just thought they looked a bit like planets. And all that's left behind is the tiny, super-dense core, a white dwarf.
High-mass stars, however, go out with an unbelievable bang. As they age, they develop this onion skin structure, fusing heavier and heavier elements in layers, helium to carbon, carbon to oxygen, and so on. This whole process keeps going until the core becomes iron. And iron? Iron is basically a cosmic dead end. Fusing it doesn't create energy. So gravity finally wins, the core collapses in an instant, and the entire star explodes in a supernova.
So there you have it. Two totally different endings. One's a quiet fade-out, the other is a spectacular explosion. But what's the big takeaway? What's the ultimate legacy of these cosmic powerhouses? What do they actually leave behind for the rest of the universe?
Well, this is their real legacy. Stars are basically element factories for the universe. Low-mass stars, they create and leave behind carbon and oxygen. But the supernova explosions from high-mass stars, they're so powerful they forge and then scatter all the heavier elements across the galaxy. We're talking about the iron in your blood, the gold in jewelry, the oxygen you're breathing right now. This enriched stardust is the raw material for new stars, new planets, and eventually, us.
And that right there is maybe the most profound connection we have to the cosmos. We are, quite literally, made of stardust. The very atoms that make up our bodies were forged in the hearts of stars that lived and died long before we ever existed. So, if that's the legacy of the stars, it leaves us with one final big question. What legacy will we, in turn, leave behind?